Today we'll be doing something quite stupid. We'll be using MS Excel to calculate and visualize the Mandelbrot set. For any proper programming language or visualization application, the Mandelbrot set is really not much of a challenge, but as we will see, the requirements for calculating and drawing the Mandelbrot set are something for which MS Excel is truly a horribly bad choice. There are many steps along the way that go against Excel's design principles and targeted use cases that we'll be needing to overcome somehow, using the bad tool at our disposal. And to make this challenge even more intimidating, we'll be using only formulas to do this. No macros allowed this time, as they would be making the needed calculations too easy. I will make a separate video later where I'll be using macros for this, but for now, only formulas are allowed. The reason for taking on this kind of a challenge is not that there would be any direct business applications of visualizing Mandelbrot sets or similar fractals using Excel, but rather we can use this as a test to see if we can coerce Excel into doing something that goes fundamentally against its nature. And if we can do this, we can be quite confident that we can tackle any and all real-life practical problems that we might be facing when applying Excel for real and for practical applications. Before whipping out Excel and starting to debug the formulas, let's have a quick recap of what the Mandelbrot set really is, and what are the specific challenges that emerge when one tries to calculate and visualize it using Excel. At the very core of the Mandelbrot set's infinitely deep and never-repeating fractal shapes is an astonishingly simple mathematical formula: x squared plus c. It's literally mind-blowing to think that a simple formula as this can give rise to all the myriad of shapes, symmetries, and similarities that we can observe in the Mandelbrot set. So, the underlying formula or mathematical intricacy should not pose any challenge for us to execute in Excel. However, the first inconvenience arises from the fact that the Mandelbrot set is located on the complex plane with real and imaginary coordinates. Excel does not have any readily available functions or tools for dealing with imaginary numbers, as the need for those rarely arises in business applications. For example, there are very few people who can do business by selling imaginary cars. But ultimately, this is not much of a problem for us. Complex numbers are nothing more exotic or mystical than a pair of real-valued components that have one special calculation rule that needs to be kept in mind. Namely, when you multiply two imaginary parts, they simply change into one negative real number. So, all we need to do is to keep track of the real and imaginary coordinates separately throughout all our steps of our calculations, and remember to apply the calculation rule that turns two multiplied imaginary units into negative one real unit. And to account for the Mandelbrot set's plus c part, for every time you square a number, you just simply need to remember to add the coordinates of the original starting point to the results. So, nothing here that we should not be able to handle in Excel. But then we encountered the second hurdle of Excel implementation. It's not enough to do this squaring only once, but we need to be doing it recursively several times. And Excel is really not the best tool for executing recursive calculations. But once again, this is nothing that we cannot handle. We simply need to organize our calculations in a way that enables recursively feeding the outputs of the previous iteration as inputs to the next round of iterations. In effect, when you apply this process of squaring the coordinates of the point on the complex plane and adding the original starting point's coordinates, the result is a new point somewhere else on the complex plane. And repeating this x squared plus c procedure again to that new point once more leads to yet another point somewhere else on the complex plane, and on and on and on. So, doing this procedure recursively to any start point in the complex plane provides us with a sequence or a trajectory of points somewhere in the complex plane. And this is where things start to get really interesting. Depending on the chosen starting point, the new points that you get from this iterative process can be vastly different. If, for example, you start from the point of 1/2 plus 1/2 I, you can see that the iterations very quickly start providing excessively large values. If, on the other hand, you start from a relatively close by starting point of 1/4 plus 1/2 I, you get something completely different. The numbers don't seem to grow uncontrollably, but rather they stay on a narrow area of the complex plane, even if we keep cranking up the iteration machine multiple additional times. We can get a better handle of this phenomena if we plot the trajectories that emerge when we start this x squared plus c iterative process from a few different possible starting points.
Using this very quick and dirty visualization tool, we can explore what kinds of trajectories take place when we start this iterative x squared plus c process from different starting points. So firstly, we can find these starting points that the results explode to infinity almost immediately from the start. But then we can also find some other kinds of starting points where the trajectories can bounce around for a while before taking the express highway. But then again, we can also find yet another types of starting points that don't seem to be leading to any exploding trajectory, no matter how hard we try, but rather the results seem to be getting stuck to some repeating trajectory. As we can see, these repeating trajectories can take very different kinds of shapes, for example, stars, zigzags, loops, and diamonds. So obviously, something very intriguing is going on in here, as very small changes to the starting point can lead to very different outcomes for the trajectories. But how could we make better sense of what's happening in here? And how could we visualize these different trajectories? And this is exactly what the Mandelbrot set is. It's a crude illustration of what happens when you start up this iterative process from different points. The Mandelbrot set visualization overlooks the specific shapes and types of these trajectories and only counts how many iterations of this x squared plus c machine are needed before the point has reached escaped velocity and is irreversibly on its way out of our galaxy. Luckily, though, we don't need to iterate every number very many times to draw the final conclusion. When we first encounter the point that takes the iteration outside the circle that is around Origo and having a radius of 2, we can be sure that this trajectory is gone and it is never coming back. And if this distance from Origo never exceeds 2, then in any of our iterations, then we can conclude that the trajectory is bound to a confined path. The starting points that lead to these never exploding trajectories are considered to be inside the Mandelbrot set, and the ones that lead to exploding trajectories are outside of the Mandelbrot set. And this we can visualize by overlaying Mandelbrot set to this graph that we have already been using. The aesthetic and multicolored halo that is typically drawn around the Mandelbrot set is made by assigning different colors to the starting points, depending how many iterations are needed before the trajectory starting from this point escapes beyond the radius 2 circle.
So, to recap, the challenges that we need to navigate today are dealing with complex numbers. This we can overcome by separating and keeping close track of the real versus imaginary coordinates and remembering to apply the calculation rule that turns two multiplied imaginary units into one negative real unit. Doing iterative calculations without macros. This we can overcome by structuring our calculations carefully. And finally, finding a suitable graph type. Overcoming this will be requiring some out-of-box thinking, but we'll be sorting this out as well. As the complexity of the calculation procedure to do all this is above average, let's do a quick flow diagram of the different elements and logics that we need to execute so that we don't get lost along the way. Firstly, we don't want to make this into a static snapshot of the Mandelbrot set. Instead, we want to be able to navigate and zoom into different parts of the set to explore what kinds of fractal shapes it holds. To this end, we want to start by giving the users the opportunity to specify what part of the Mandelbrot set they want to focus on. As the screen size of most computers have more horizontal width than vertical height, we want to be able to exploit the screen as effectively as possible, so we want to provide the user with the choice over the aspect ratio. Secondly, as the calculations can be quite heavy and take time to complete, we want to offer the user the possibility to get faster results by lowering the resolution and increasing the resolution once the desired location of the Mandelbrot set has been found. Then, we want to offer the user the chance to select what region of the Mandelbrot set to focus on. And finally, the user can select how detailed a zoom they want to apply to that location. After these inputs are provided, all the following steps are to be fully automated using formulas. Next, we need to generate the complex plane start points, meaning their real and imaginary coordinates, based on the given user inputs that we need to evaluate and visualize in the following steps. Then, for each of these start points, the formulas need to execute a sequence of iterative calculations. Firstly, to check if the current distance from origo is above 2 using Pythagorean formula. And secondly, to check if the maximum number of iterations has already been exhausted. After these iterations, the formula should provide one escape speed number to match each starting point's coordinates, either telling that how many iterations it took to escape to the orbit, or 0 if the results never began exploding in our iterations, meaning that the start point is inside the Mandelbrot set. Parallelly, as Excel's readily available graph options are not meeting our needs, we need to be creating our own visualization template right from the add-ons. And finally, once you have the visualization template ready and the calculated results for the number of iterations it takes to escape from any given start point coordinate, we need to be pulling all this together and visualize the Mandelbrot set. Easy peasy. Now, we're ready to whip out Excel and roll up the sleeves.
So let's start by asking user that how tall and how wide a picture they want to visualize. And for this, we're talking about the aspect ratio. And remember, in the complex plane, the horizontal direction is the real axis and the vertical direction is the imaginary axis. And let's give some dummy numbers so that we can later on check that everything is working nicely. Then, secondly, we need to be defining the visualization area. And for this, basically, we need to be asking user to provide the corner coordinates of the visualization area. So basically, what we are talking about in here. So if this is the area that they want to visualize, then we need to be asking that what is the top left corner coordinates and bottom right corner coordinates. And here in the top left, we are talking about the minimum of real axis and maximum of imaginary axis. And on the bottom right, we're talking about the maximum of real axis and minimum of imaginary axis. So basically, once we know these coordinates, we have defined the visualization area, and we can then proceed on using that in later calculations. So, and we don't need to be asking user to provide this minimum imaginary number, because we can calculate that based on the other three inputs that we are already requesting. So let's just put some dummy numbers in here so that we can continue or use those in the debugging. So let's use -2, 1, and 1, because majority of Mandelbrot sets action is taking place inside this area. So let's then tidy things up a bit so that everything stays nice and clean. Okay, and with that, we are done with the user inputs. After this, everything else should be fully automated. But to make our own work later on a bit easier to use and easier to build the formulas, so let's clean things up and calculate a couple of numbers that we'll be using in the later on calculations. So first of all, we need to be specifying the amount of start points that we need to be dealing with. And this is nothing more complicated than multiplying how many, what's the horizontal and vertical direction. And in this case, it's we only have 150 starting points, so very low, but for our debugging purposes, that is enough for now. Then we need to be calculated that what is the increment that when we move from one start point to the next one. And that is once again nothing more complicated than taking the maximum of real and then subtracting the minimum of it. And this change of real value axis takes place on this many increments. Sorry. And each of these increments then is about 2. But actually, this formula is not fully correct because we need to be accounting for the fact that Excel is taking the first row to be the kind of a zero index row. So we need to be subtracting 1 from here. So the actual increment that takes place between our starting points is 0.214 in this particular case. Then let's just pick these real and imaginary numbers here so that we can use them more easily. And then when we want to find out that what's the minimum of imaginary numbers, then we simply need to be starting from this and going down 10 increments with each of having the size of 0.214. But once again, this is not yet fully yet ready because we need to be accounting for the fact that the first row is already accounted for as the index of 0. So we need to be subtracting 1 from here. So actually, when we go down 10 times, starting from this height at the increment of 2.214, we end up on the imaginary value of negative 93. So let's then clean things up just a bit. And with that, we are done with the user inputs and we are ready to move on to generating the start points. So, in order to be able to draw the Mandelbrot set eventually, we need to have a combination of 3 numbers. So first of all, we need to be knowing that what is the starting points, real and imaginary coordinates, and then we need to be knowing that, okay, from starting from this point, what is the escape speed, that how many iterations is needed when starting from this point before the distance exceeds the radius to circle. So we need to be generating these starting points and so that we can then continue calculating these escape speeds. So the game plan for generating all these starting points that fill the user-specified visualization area is that we start from the top left corner and then generate the starting points that have the same imaginary value and increase the real value until we hit the maximum of real values, and then we reset the real value coordinates and decrease the imaginary coordinate by one increment. So basically going one row lower and then going all the way once again to the right until we hit the maximum of real, and rinse and repeat all the way until we finally hit the bottom right corner that has the maximum of real values and minimum of imaginary values. So we need to be kind of starting from the top left corner, meaning the minimum of real axis and the maximum of imaginary axis. And also we need to be kind of making sure that we are able to keep track that which starting point are we actually talking about. So we will be needing a what I call a start point ID. And this is nothing more complicated than just a running number that starts from 1 and keeps adding 1 until we have exhausted the amount of needed starting points. So as long as the previous starting point is less than what we need, just keep adding, and otherwise just do not bother. Okay, so and then let's first deal with the real values. So first of all, so the idea is that we need to be increasing the real value component one increment by one increment until we hit the right side of the visualization area, and then we want to reset it back to the start. So as long as the next iteration is still within the visualization area, we should be increasing the real value by one increment. And if not, if the next point would be taking beyond the visualization area, then we just reset back to the start. Okay. So this seems to be working nicely. So we can see that the real values keep increasing until we hit the maximum of real value, and after that it resets back to the minimum of real values and then starts again the same process. So we need to be now doing something similar for the imaginary values. So the game plan in here is that we want the imaginary coordinate to stay the same until it spots that the real value has been reset, and then it should be just subtracting one from the one increment from the previous imaginary values and then continuing it as it is. So if it spots that the real value has been reset, then it should be subtracting one increment out of it. But if that is not the case, then it just should keep whatever is on top of it. let's see. And once again, we can see that it's working nicely. So that we can see that it keeps the same imaginary value until the real component has been reset, and then it just goes down one increment and keeps repeating it again and again. So let's then now keep adding a few more rows for us. Okay. And we can now see that our formulas are not fully robust yet. So even though the amount of needed starting points has already run out, these formulas just keep generating new start points even though we don't need them. So that's not a very useful way of spending excess resources. So let's kind of make the formulas a bit more robust for our needs. So let's, and this is nothing more complicated than just checking that if we have assigned a start point ID, then it should be calculating that what's the next start point. If not, then just do not bother. And then similarly also for the imaginary coordinate. So and then when we go to the bottom, we can see that the starting points stop generating after we have exhausted all our needed starting points, and we can see that the bottom right corner coordinate is has the real value of 1, which matches in here, and then imaginary coordinate of minus 0.93, which is once again matching what we were expecting. So it seems that our formulas are working nicely in here. So let's just then keep adding a few more starting point, at least the placeholders for us, so that we can keep using those later on in our calculations. Okay, and with that, we are done with the generating of the start points. But we can do one more checking that have we really been able to implement this logic that we were trying to do. So we can do it very simply by making ourselves a graph to see that does this work. But we should of course be using only the rows where we have data, because otherwise the Excel's scatter plot just does not want to play ball with us. And here we can see that this start point generation is doing exactly what we want it to do. So it just keeps adding or increasing the real values one increment at a time, but keeping the imaginary coordinate the same. And then it resets back to the minimum and goes all the way to the right, one step down, all the way to the right, one step down. So our start point generation logic seems to be working nicely, and we are ready to move on to the doing the iterative calculations that what happens when we subject or start from this starting point and start cranking up the x squared plus c iteration multiple times after this. So the next point that we're needing to be doing is doing the iterative recursive calculation to see that how many times do we need to crank up the x squared plus c iterations before the distance when starting from each given starting point takes its beyond the radius 2 circle. So first of all, we just need to be able to calculate that how far are we actually from the origo at a given point that we are talking about. And this is nothing more complicated than using the Pythagorean formula, which is just uh, taking the square root of the squares of these numbers, sum of the squares. And in this case, we can see that this point's distance is already 2.45 from origo. Okay, but then we are not actually exactly interested in the absolute distance of that, how far this point is from origo, but we are just interested to know that whether this distance is above or below 2. So we just can use simplify the results by just checking that if this distance is under 2, then it should be giving us a 0, and otherwise if it's beyond the radius to circle, it should give us a 1. And we can see that a couple of our starting points already in the top are already beyond this radius to circle, but some are not. And then we need to be kind of starting to do the iterations and just cranking up that, just refeeding these starting points and previous iterations to this iteration logic, where we just are taking the previous iterations coordinates, squaring it, and then adding the original start point coordinates to it. So first of all, let's just keep track, make sure that we can keep track of which iteration are we talking about. And in the first case, we are talking about iteration number 1. And the formula that gives us the next iteration's real component is here. So basically we need to be squaring the previous iteration's real component, subtracting the square of previous iteration's imaginary coordinate, and then remembering to add the original iteration's real component. So let's just type that in. So squaring the previous real, subtracting previous imaginary, and then adding the original start point's real coordinate. And that's it. And then similarly for the imaginary coordinate, we need to be just doing the same, but with a slightly different formula. So in order to get the next iteration's imaginary coordinate, so we just need to be using the formula of 2 times previous iteration's real coordinate times previous iteration's imaginary coordinate plus original start point's imaginary coordinate. Like so. And then we just need to be calculating that what is this new points distance from origin. So I have a error in the formula. So it's this is not a plus, but it is multiplication. And with that, we can see that, okay, for example, that this point was not beyond the radius 2 circle immediately, but already the first iteration beyond that took it beyond the radius 2 circle. So the formulas seem to be working well, but they are not as efficient as they could be, because we are not basically interested in these numbers at all, because we already know that the first starting point was already beyond the radius 2 circle, so we don't need to do these iterations. We can stop them for these. So we can do this very simply, that we add an additional condition in here. So only if the previous iteration has this distance label value of 0, then it should be doing the calculations, and otherwise just leaving itself empty. And then similarly in here. And in here we can just do this, put this inside this if error catching mechanism, that in case it does not seem to be working, then just leave it empty, don't give us any error messages. Okay, so let us okay, we still seem to be having some robustness issues with our formulas, and it's coming from here, so we need to be doing the same using actually this formula for everything. Okay, and now it seems to be working well. So now that we have calculated the next iteration, the remaining additional iterations are just kind of a copying and pasting this as many times as we need it. So now we have 40 iterations, or placeholders for 40 iterations, and then we could basically choose a number that's higher or lower, but 40 iterations is plenty enough to do really high quality, high resolution, and vivid images of the Mandelbrot set. And here we can see that we can see some starting points that even after 40 iterations, the distance just does not seem to be getting anywhere. It does not seem to be going beyond the radius 2 circle. And these are the starting points that are assigned inside the Mandelbrot set. And then the other iterations are then something that or have escaped the Mandelbrot set or this radius 2 circle at some earlier stage. So we can see in the beginning that these two kind of original starting points were already immediately beyond the radius 2 circle. And then we can see that these additional starting points escaped the radius 2 circle on the iteration number 3 and the on number 4, number 5, and so on. So it seems that our calculations are kind of starting to paint a quite interesting picture. And now we just need to be kind of summarizing all these iterations up into this escape speed column. So we need to be kind of picking up that which iteration was it that took this starting point beyond the radius 2 circle. And since we have built our formulas in a way that allows that there can be at most one instance where the distance column has a number of 1. So we can use some ifs formula to do this. So it should be summing this range on the criteria that first of all we are only interested on the columns that have the label of dist and that the value in here is 1. So that we can see that it correctly identifies that these two first starting points escaped at iteration number 1. For this particular one, it took 10 iterations before it escaped the radius 2 circle. And then let's see if we can find, for example, this starting point in here provides a escape speed of 0, which we interpret to mean that it did not escape at all. So even after 40 iterations in here, it still does not seem to be going anywhere. So we'll be assigning this inside the Mandelbrot set. And with this, we are done with the generation of the all the information that we need for drawing the Mandelbrot set. We have the starting point coordinates, and we have the knowledge of which how many iterations it took to escape the radius 2 circle from these starting points. So with this, we have all the data that we need, and we can now move on towards visualizing the results. Okay, now we have all the necessary piece of info and the data that we need for drawing the Mandelbrot set. So first of all, we have the starting points, the coordinates, and the knowledge that how many iterations it takes to escape beyond the radius 2 circle. So, and in order to have a bit more resolution in a picture, I've adjusted the aspect ratio and the kind of amount of start points to 150 and 100, giving me a total of 15,000 start points to visualize. So let's first of all explore that how far is Excel able to carry us with its base case tools. And the most readily available and feasible visualization tool for drawing this kind of Mandelbrot set that Excel provides to us is the scatter plot. So let's explore what it can and cannot do for us. So let's start by creating a new sheet where we will be collecting the data, organizing it in a way that the scatter plot can be drawn. So basically, we need to be collecting all the starting points that have the same escape speed 0, 1, 2, and so on, and then have those as their sets of their own so that we can draw them separately and have a specific color assigned to them, and then moving on to the next set of starting points that have a different escape speed. And we can do this using the filter function. So we want to be filtering our set of start points real axis coordinates on the condition that our escape speed column is having the value that we are currently interested in. And similarly, we need to be picking up that what are the corresponding imaginary axis coordinates. So instead of picking from column C, we need to be pick from the adjacent column D. Nothing more complicated than that. And let's do a couple of more iterations. Just to kind of give the idea that where this approach would be taking us if we would really want to be using it. And in case you really want to try to fine tune this, so you would be able to kind of tidy things up a bit by adding this trim range functions around it. But since we will be abandoning this approach quite soon, so let's not spend too much time in fine tuning this. So, and then we can move on to actually drawing the scatter plot with the data that we have fetched in here. And just by adding this iteration 0, we can see that something that's taking the shape and size of the Mandelbrot set is beginning to take shape in our illustration. But let's add a couple of more of these different iterations to kind of show that where this would be taking us if we would be kind of exploring this further. Okay, so no matter how hard we try, this is not never going to be able to provide us with a very easily usable and visually pleasing way to visualize the Mandelbrot set that we would be able to kind of keep dynamically updating and keeping itself clean when we start playing around with these different user inputs. So we need to be kind of taking a step back, thinking things again, and see that how we would be able to visualize the Mandelbrot set in a dynamic and visually pleasing way, because we can do better than this. So, what can we do if the best what Excel has available for us is just not good enough? Then we can, of course, create a visualization template of our own, starting from the scratch. And the idea behind this is that we will be using Excel's cells as pixels in our graph. Let me show. So we'll be using the building a visualization template that is using the individual cells as pixels, and then having a certain way of assigning IDs to these cells. And based on the ID that we have in the visualization template, it then goes back to our data and finds the correct start point ID that corresponds with that pixel, and then fetches the corresponding escape speed number to that pixel. And then, based on whatever number has been fetched to that pixel, we will be using that as a criteria for choosing the color for that pixel. So, first of all, let's just make sure that debugging is a bit easier. Let's drop down the resolution a bit for us. So let's return back to the 15 by 10 for temporary purposes. Then we need to be kind of creating the axes of this graph so that we can use that in our later calculations. Okay, and now we need to be generating the cell point starting point ID for this cell. And the idea is that the first row's IDs would be corresponding to numbers 1 to 15. Second row's numbers would be from 16 to 30, and so on. So basically following the same kind of logic that we applied in the datasheet. And this we can do by simple calculation. So first of all, we just need to be checking that which row are we on. So first of all, we are on row number 1, and since the first row does not need to be having any additions, so we need to be just subtracting 1, and then whatever is then left, we just need to be multiplying that with the amount of times we have gone through all the horizontal values. And then for that, we need to be just adding whatever is the column header that we are operating in here. So this is now working nicely, so that the first row is having the cell start point IDs running from 1 to 15, second has to from 16 to 30, and so on. So let's just make sure that our formulas are robust, and let's keep adding a couple of new ones here. Nope, they are not robust. Okay, and now that we are able to have the corresponding coordinate information found in here, so we need to be using this as a criteria to match this and fetch information from here. And this is the fastest formula for doing that is index match. So we need to be picking up stuff from here on the condition that the lookup value that we just calculated is found on the list of start point IDs in our data. And we are only interested in the exact matches. And let's see. So for example, the start in here we should have on the 4th row and the 7th column we should be having a point that took 36 iterations before it escaped. And that corresponds to cell ID 52, which is matching nicely in here. So then the next part that we need to be doing is that once we have been able to label our cells, fetch the correct escape speed. Now we need to be using that as the criteria for coloring these cells. And in here, so there could be a possibility to create some super convoluted hexadecimal calculations to dynamically do color ranges in here. But the easiest way that I found to do this is that we just use conditional formatting. So we just assign a different set of conditional formatting. That's very fast to do. It takes only a couple of minutes, and it gives you full visual control over which color schemes you want to use. And that I've made this kind of a color scheme in here. So basically, just to spare you from the kind of a mundane repetitive tasks. So basically, all this is done is that I have assigned different kinds of conditional formatting values based on the escape speed numbers that I have, and just visually I just started by assigning black color to the cells that have zero as values, white where it's kind of is immediately beyond the range, and then kind of gradually changing from one color to another. And since we did our calculations up until the point where we have all the way to 40 different iterations, so let's just add a couple of more iterations to our conditional formatting in here. Applying the different formatting in here, so we can see that the new values that we added are now covering all the way to iteration number 40. So all that's left to do is that we just simply copy the formatting of this and then apply it in here. So as you can see that something very, very crude and vaguely resembling the shape and size of a Mandelbrot set is starting to take shape, and that now all that we need to do is to realign the horizontal widths and vertical heights of this graph so that it's kind of a smaller, the pixels are smaller and equally wide and equally tall, and then just keep adding multiple more to the horizontal and vertical direction. And as you can see, the Excel's logic of assigning widths and heights to cells is not aligned, so that in order to have 5 pixel wide cell, you need to be having a width of 0.42, and if you want to be having a 5 pixel wide height, you need to be having a height of 3.75, which is weird, but that's what it is. Then what we now can do is that we can crank up the resolution and see where it takes us. And here we go. As you can see, this kind of a way of rebuilding the visualization right from the scratch gives us a lot of opportunities to play around and control the graph in a much more dynamic way. So all that's now left to do is that for us to play around with the user inputs and see how it corresponds with the graphs that we do. Okay, now we're finally ready to move on to the last and most fun part of this all, meaning playing around with this tool and the zooming options that we have built and see what kind of structures the Mandelbrot set reveals to us when we start looking at it more closely. So first of all, we need to be kind of making sure that since every iteration and calculation that we do is actually triggering quite a lot of calculations, so let's make sure that it doesn't trigger those until we have set up all the parameters for the calculations, so that we don't spend too much time waiting. So let's go to the calculation options and put it to manual so that we can trigger the calculations only when we need it. So in the meanwhile, I've been kind of doing a bit of a adjustment to this calculation principle or this template so that now we can account for a picture that has at most 300 columns of width and 150 rows of height so that we can get a bit more granular resolution of our picture. So then, first of all, we need to be selecting that which part of the Monte project we would like to be examining more closely. So, for example, if we would be wanting to study this part more closely, that what this bulge here contains, we first need to be kind of finding the coordinates for this, and it's a bit of an iterative process. So let's keep the resolution down for a while, and then when we have found the correct coordinates, then let's crank up the resolution to max. So let's first of all try that. What does it look like if we would be setting the real axis minimum to negative zero point 0.3 and the positive maximum of positive zero point 0.3. And since our maximum resolution is having 300 width and 150, meaning half of that in height, so let's make sure that when we crank it up, so this change of aspect rates ratio does not mess up our picture later on. So let's see what this picture looks like if we would be using these as our inputs. Okay, it's getting closer, but I personally like to have a bit more on the bottom side of this bulge available, and then a little bit less of this boring stuff on the right available. So let's change the parameters for a bit to see where that would take us. So I'm happy with the real axis minimum in here, but then I would want to have a bit less on the right. So let's put that to 0.2. And then actually let's crank up a bit of this aspect ratio downwards so that we can get a better handle of what's happening on the lower side of this graph. Okay, this is looking much better. So this is actually good enough for now. So let's then move to the next part, meaning cranking up the resolution all the way to the max that we can do with this kind of a aspect ratio that we have chosen in here. So we will now be limited by this ratio because we can have at most twice the amount of pixels on the vertical axis compared to what we have on the horizontal axis compared to what we have on the vertical axis. Okay, so now this is bringing much more closer details in view, but still this resolution is limited by the size of pixels that we have chosen in this Excel cells. So right now we have been using 5 pixel wide and y pixel tall cells for our illustrations. So we can actually make this even more crisp by changing these cell widths and heights to be smaller. So we can set the column in order to have 1 pixel high columns and 1 pixel wide cells, we should be setting the column width to 0.08. And then we need to be setting the row height to be 0.75. Okay, and that gives us the picture on the bulge that we're trying to do with this 1 pixel by 1 pixel resolution, which is giving a bit more accuracy for us. And now, kind of the only kind of a limitation that you have for doing deeper and deeper drill downs is the amount of patience and memory that you have on your computer for drawing this picture. And as you can see, that even though we have disabled the automatic calculations, all these steps are getting quite slow. So we are already kind of pushing the boundaries of what the formula-based Mandelbrot set is possible to do in the Excel. So the next step forward would be to actually abandon formulas altogether and do this same exercise but using macros. So that's the focus on the next video that we'll be doing. So showing how much easier and how much faster and we would be able to do this with macros and how much bigger and higher resolution pictures we can do if we choose to use macros instead of formulas. So hoping to see you joining up also to view that video.